Let's go through Lincoln 979 distribute counts in binary tree. For this question, it gives us a binary tree, and for the binary tree, it has a attribute called value. Means in this node there are n this value number of coins, and totally there are n nodes and also n coins. It asks us how many moves we need to take to make actually return the minimum number of moves to make every node has exactly one coin. So for this, let's look at this example, right? So at the beginning, at the root, there are 3, right? And on its left, it's 0 and 0. In order to get it evenly distributed, we should move one to the left and move one to the right, right? So that all of this will have one coins. So for this kind of question, how can we do? How can we analysis actually? Let's look at the second example, right? You see this is 3. Actually, we should move out 2, right? So this becomes 2. And this one we should move in 1, right? So this well, so this one will move out 2, and this one move in 1, right? So this will be 2 plus 1. So if we look at the second example, right? So we think about move out and move in. You see, for this node, it has 2 coins extra, right? So that means we needed to move out 2 coins. So that means we should there is 2 moves in these edges, right? And for this coin, this node, it has 1 less, right? Then that means we need to have move 1, right? In this kind of path. So the absolute value of the unbalanced in this subtree will be how many moves on this way edge. So what we're thinking about is that for every nodes, right? Every nodes, every tree, let's look at this kind of tree. It has a left subtree and a right subtree, right? We use some kind of Debye-Quankel or DFS return for this kind of the subtree ended with this node, how many coins, actual coins, right? So if it is more than what we need, for example, this will return a positive number. And if it is less than what we need, then this is a negative number, right? So the thing is that how many the moves on this edge will be the actual number, or we need to move in the less, right? So we use DFS to calculate the sub left tree and the sub right tree, right? So so we know in the user Debye-Quankel, we can also for example, this d is greater than 0, right? That means we are going to move out this kind of d to this root. If this is d smaller than d right smaller than 0, we are going to take this d right to its right child, right? So in the end, what for this kind of node, right? So this tree, what is the actual balance? Let's say actual balance we left is this d left plus d right, and plus this value and -1. Why should the -1? Because of this, we should also keep one coins, right? So this is return for the DFS is return the balance end with this node, whether it has actual coins or less coins, right? And for our moves, no matter this is actual or less, right? The moves the moves for these nodes to its parents will be this absolute value of this, right? So if this is, we have, for example, let's look at the left. If we have 2 actual, right? So we need to move out 2, right? So we should add 2. If this is -2 on the right, right? So we should move in 2, right? So for this pass is 2. We don't care about the sign, right? This pass, this is also 2, right? So there are 2 moves here, these 2 moves. So we sum up on the edge is the moves. So let's begin to write code for this. We know the result. We need to get a result, right? We need to pass it in reference. So let's have result equals new int 1. Okay. So what we do is that we just DFS root result in the return result there, right? And private int DFS. This DFS we return the balance for this node, for this tree node. The balance, right? So we'll say if this kind of node equals to null, right? We just return the balance is there, right? Otherwise, we'll see we call balance, okay? Balance. That is the tree with this root, right? Whether we have actual coins or less coins, right? So that will be DFS node dot left result in the class DFS node dot right result, right? In the class node dot value. And for this kind of root, we should keep one coin, so we should -1, right? So our result is for this kind of node, right? The result, how many moves that will be on this edge, right? We should have an absolute value of this balance, right? And we return this one for the root, right? The root because they are balanced. I mean, the whole tree is balanced, so the root there is no coins outside and more inside, right? So that will be 0, right? So for the last one, that we don't need to care about result, update the result, right? So result should plus equal to mass dot absolute value balance. And in the end, we return. This is a reference and array return balance. And the Python code should be very similar, right? So we define DFS. DFS should be node optional tree node, and we should have a result. Let's have this as a list director, and it returns an int. So I say if not a node, if this is not null, return, or if this is null, return 0, right? And we are going to have move balance equals DFS node dot left result plus node dot DFS node dot write result and plus node dot var and -1, right? And we should have result there plus equal to absolute value balance return balance for our DFS is return balance. And for main, right, result equals this, and we have DFS root result, and the return result 0. Okay. And the time complexity will be O(n).